Hey everyone, it's now time to talk about the last major physics topic in this course. It's called entropy. Now, entropy is a little bit of a buzzword, and you may have heard of it before. The analogy that's usually given for entropy is that it's a measure of disorder in a system. Now, this is fine as sort of a popular science explanation, but we can do better than that. Entropy is a statement about the microstates of a system. To start, let's just do a brief recap of what we saw last time when we talked about microstates and macrostates. We talked about macrostates as sort of like the big picture stuff that we can measure about a system. For example, if you have a box of gas, the macrostate would be the pressure, the volume, the temperature of the gas, and so on. The microstate of the gas would be the specific configuration of individual particles in the gas. That would involve the positions and locations of every single particle. We said that the probability of a macrostate depends on how many microstates give you those numbers. Exactly which configuration of particles your gas is in doesn't really matter at the end of the day. The important thing is the macrostate that you can measure. But if you want to make a prediction about which macrostate your system is most likely to be in, you do need to know something about the microstates. Specifically, you need to know how many microstates will give you the particular macrostate. The more microstates will give you a particular macrostate, the more likely it will be that you'll find the system in that macrostate. Now, we don't have time in this course to actually learn how to calculate the number of microstates that a box of gas, for example, will have. It can be done, but the math is really involved and complicated. Entropy is just a number that describes how many microstates are available to a system. For a system with very few microstates, the entropy will be low, whereas for a system with a large number of microstates, entropy will be high. Thinking about microstates allows us to make sense of why gases behave in particular ways. In the last video, we talked about the case of a box with gas in it where all the gas had been shoved up into one corner of the box. Now, this is never going to happen naturally. The gas is always going to spread out to fill up the entire box. But this is not because the gas can't go up into the corner. It absolutely can. But the number of microstates that involve all of the individual particles of the gas shoved up into one corner is incredibly small as compared to the number of microstates that involve the gas spread out evenly throughout the box. Because of this, the case where the gas is spread out evenly is just so much more probable than the case with all the gas shoved up into one corner. But now we know something about this thing called entropy as well. It is also true to say that the entropy of the gas when it's spread out evenly through the box is much greater than the entropy of the gas that's shoved up into the corner. This turns out to be a general result, and it's called the second law of thermodynamics, and we'll look at it a little bit more in the next video. But we can also think about another case that we've seen a lot in this course. Imagine two substances at different temperatures that are exchanging energy. Now, we've always said that heat flows from the hot object to the cold object, and that's true, but this is actually very similar to the case of a box of gas. If you have two objects and one is hot and one is cold, and you put them together, you can think of it sort of like you've shoved all the particles in the box of gas up into the corner. The objects are going to exchange energy because there are way more microstates available with the two objects at the same temperature than there are with the two objects at different temperatures. And so, over time, the system is going to tend toward the state where the two objects are at the same temperature, just as the box of gas with the gas shoved in the corner will tend toward the state where all the particles of gas are spread out. Now, there is an equation that we have that allows us to calculate the exact entropy of a system. It looks like this. It just says that the entropy of a system is equal to the Boltzmann constant multiplied by the natural log of omega. But what is omega? It just tells you how many microstates are currently available to the system. Now, again, you're not going to be asked to compute this number, for example, the case of a box of gas. But it's good to see this just so you can know how the two numbers are related. Now, notice I said the number of microstates that are available to a system. To go back to the box of gas example, let's imagine a system with a box of gas where there's a partition down the middle. All the gas is on one side of the partition. If the partition wasn't there, we would expect that the gas would expand to fill the entire box. But the partition is there, and so even though the box is bigger than the volume of the gas is confined to only half of the box. In physics, we call this a constraint. There's a constraint on where the gas can be, and that limits its entropy. But that if we then removed the divider from the center, the gas would expand. The constraint has been removed. There is still a constraint on the gas. It cannot get bigger than the volume of the box, but the constraint is less restrictive than the previous constraint, and the entropy of the gas is going to go up as it expands. The primary thing we're going to be concerned with in this course, though, is calculating changes in entropy for certain processes. There are two cases that we need to be aware of. The first is the constant temperature case. If you have a process where the temperature of a system is not changing, then you can calculate the change in entropy just by looking at the heat that goes in or out of the system during the process and dividing by the temperature. An example here would be a phase change. When a substance goes from a solid to a liquid, its entropy increases. If you could calculate the amount of heat that went into the system during this process and then just divide by the temperature, then you would get the change in entropy. One thing to note here, this temperature always has to be in Kelvin. You could see why by just thinking about ice. Ice changes phase at 0 degrees Celsius. If you plugged 0 into the equation Q over T, you would get, well, an undefined answer. So whenever you're working with entropy, make sure that the numbers that you're plugging into your equation are in Kelvin. But this equation only works when temperature is constant. What about the case of, say, an object that's warming up or cooling down? Well, we actually have an equation for that case too. It looks like this. It just says that the change in entropy for the system is equal to the heat capacity of the system multiplied by the natural log of the final temperature divided by the initial temperature. Now, maybe you don't remember exactly how natural logs work, but natural logs are positive if the number inside of them is greater than 1, and negative if the number inside them is between 0 and 1. You can't take the natural log of a negative number, so we always have to use Kelvin here as well. Kelvin is always positive, and so if you plug in two positive numbers and divide them, you'll get another positive number. Crucially, if the final temperature of the system is greater than the initial temperature of the system, then the natural log will be a positive number, and the change in entropy will be a positive number. If the final temperature of the system is less than the initial temperature of the system, then the number in the natural log will be less than 1, and the change in entropy will be negative. This sort of matches with what we saw from the previous equation. In the previous equation, we knew that if energy is going into the system, that the entropy is increasing, and if energy is coming out of the system, the entropy is decreasing. The same thing is true here. When the temperature increases, energy is going into the system, and the entropy increases. Now, of course, calculating changes in entropy still requires you to know how to calculate other things. For example, if you want to calculate the entropy change for a phase change, you need to know how to calculate how much heat goes into or out of the system during the phase change. If you want to know how to calculate the change in entropy for a system that's temperature is changing, you need to know how to calculate the heat capacity of the system. The heat capacity is, of course, just the specific heat multiplied by the mass. And you also need to know the initial and final temperatures of the system. Maybe they'll be given to you in the problem, or maybe you'll be asked to calculate them, but you need them both if you want to be able to calculate the change in entropy. This is the sense in which physics is totally cumulative. Entropy is a new concept. We haven't seen it before, but it still relies on our understanding of older concepts for us to do these calculations. Now think back to the examples of entropy that I mentioned previously. For example, the box of gas with the divider down the center. When we remove the divider, the gas expands and its entropy increases because there are more microstates available to the gas where the gas is evenly spread out throughout the entire container than there are microstates available to the gas when the gas is all on one side of the container. This increase in entropy is actually a law of nature. We call it the second law of thermodynamics. We'll spend a few minutes learning about what this means in the next video. That's all for now. See you next time.